So now we have discussed how the I²C real-time clock works, as well as the general I²C messages that you use in order to talk to I²C devices like a real-time clock. So now how do we go about emulating this on a PIC microcontroller? If we recall the block diagram from earlier of the I²C real-time clock, we saw that it consisted of three parts. The RAM, which is on the right, the oscillator that clocks when the RAM is updated, as well as the I²C bus interface. So all that we need to do in order to emulate this in our microcontroller is to model this system in our microcontroller. This slide shows our PIC microcontroller implementation. Like the block diagram of the I²C real-time clock calendar that we saw before, it also consists of two parts. First is the synchronous serial port module, which is able to receive I²C messages over the serial data and serial clock lines. The I²C firmware state machine interprets I²C messages received over the I²C bus, and then reads and writes this data to the real-time clock firmware RAM. We won't have time to discuss the details of the I²C slave mode firmware here. However, another webinar will be released that covers the subject in far more detail. And there's also an application note that exists with some additional details. The application note is AN734. The second part of the real-time clock implementation is the real-time clock firmware. Like the previous block diagram that we saw, the PIC has a low-power timer 1 oscillator that interfaces to timer 1. The real-time clock firmware is able to generate interrupts once a second, which we can use to update our time data. The real-time clock firmware accesses the timer 1 peripheral and general purpose registers. The general purpose registers need to be structured so that the I²C state machine can access the entire register map of the real-time clock. In this slide, we see that we must ensure that the data is grouped together in our GPR and that an additional register is added to the array. This register holds the index or offset location. This next slide shows the RAM definition for the real-time clock. We first define the length of the buffer, which is 14 bytes long. In the following lines of code, they individually assign a name as well as the offset from the buffer location of each data in RAM. So this ensures that our data is sequential and that it can be accessed by our state machine. And it also makes it easier for us to code. Our real-time clock firmware uses the timer 1 module to generate an interrupt once a second. Shown in this slide is how we go about generating an accurate time base. In order to generate a 1-second interrupt using an external 32.768 kHz crystal with no prescaler, we must preload the value 32768 into the timer registers. However, the timer 1 interrupt processing actually takes some time to execute. Therefore, we actually just set the most significant bit of the timer register, which essentially adds 32.768 into the timer 1 registers, which actually factors in any delay that may occur in the ISR. So now that we have discussed the timer 1 and general purpose register details, the next step is to use these to update our time data properly. This is an overview of the real-time clock firmware. All of the time updates occur in the ISR. Therefore, the first step that we must take when we get a timer 1 interrupt is to clear the timer 1 flag. Next, we preload the timer by setting the most significant digit of timer 1. This ensures that the next rollover/interrupt of timer 1 will occur in 1 second. Next, we check the status and configuration registers to determine our operating conditions. There are two configurations registers used in this case, even though there are only 3 bits that are actually used, because the RAM structure is emulated from an existing device. These registers determine whether or not the real-time clock is on or off, or if the alarms are on or off, as well as if any alarm conditions have occurred. The final step in our firmware is to increment our time variables. Because our time base is 1 second, the first time data that is incremented is seconds. If we reach 60 seconds, we must clear seconds and then increment our minutes. So we have to step through all our time data if we roll over, and we check each variable and determine if they have overflowed. If they haven't overflowed, then you can return from the ISR. But if they have overflowed, you need to increment the next time data value and clear the one that just overflowed. The firmware itself is very simple. It consists of just 4 steps. First, it executes at a set time base using the timer 1 peripheral. Next, it checks status bits to set operation modes of the device. Next, it increments the time variables, storing this data to RAM that can also be read by the I²C state machine. There are also a couple of things to take note of, however. In incrementing the days, you must check the month and the year, since the number of days in a month differs. And you also need to take into account leap years. And this can all be done in software. This is all we have for you today. However, we actually have some existing development tools that demonstrate what we have learned here. Shown on this slide is the PIC System Management Kit that includes a development tool that emulates 4 I²C slave devices in one microcontroller. It also includes the PIC serial analyzer, which can communicate to serial devices through a PC GUI. It also includes the firmware source code for the PIC System Management Board, as well as detailed slideshow presentations and labs to exercise the hardware. So that's all we have for you today, and I thank you for listening.